A sine wave graph is a great tool for helping to understand oscillations in more than one way. Let's begin with the case of a spring oscillating system and see how sine waves help us understand how that works. Let's imagine the spring oscillating system. We've got a block on a spring and it's oscillating backwards and forwards. It has an x displacement that goes between -10 centimeters and 10 centimeters, backwards and forwards like this. Zoom, 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 zoom. That's great. Let's even give it some numbers so we can calculate the period. Let's give it a k value and a block mass. Let's say that the k value is 200 newtons per meter and the mass of the block is 500 grams, 0.5 kilograms. We can calculate the period. Remember the period formula? The period is 2 pi square root m over k, so we can put those numbers in to calculate what the period of this system will be. The period is 0.31 seconds. That's the time it takes to go from this position to the right and backwards to the left, one full oscillation. I'm going to take that number and just leave that up there for the sake of my graph in a second. So we've got the period is 0.31 seconds. Now, when we think about the position time graph, we're going to plot the position of this block across time, and what's going to happen is it's going to perfectly make a sine graph as we plot it. So let's do that. So I'm going to try and draw two periods here, and I'm going to try and be smart about what I put on my x-axis, which is time, and what I'm going to put my y-axis, which is going to be x, the displacement. So for this block, the maximum positive displacement happens over here, where x is 10. So I'm going to put that on my y, and my maximum negative displacement happens here. So I'm going to put that at -10. I'll write it as 0.1 for meters, and -0.1 for meters. And now when I think about time, one full period is 0.31 seconds. So I'm going to write that in the middle. And this is going to get me one period, and I'll do another one to get two periods, so 0.62 seconds. So I just want to divide this in half. That's going to be 0.155 seconds. Okay, so now I'm going to draw the points that correspond of the x positions to the block. Now I'm going to start here. The first spot is going to be x is -10 when time is 0. The next spot is going to be here. This is going to be 1/4 of the period, and x is going to be at 0. At halfway of the period, it's got to here, x is 10. At 3/4, it comes back here in the middle. And then one full period, it's made it back down there. So I can try and make this into a curve. Very good. So all I did was think about the times and positions. Where is this block at different times? So at time is 0, it's there, and in one full period it goes back. So we break it into quarters. 1/4, another quarter, another quarter, another quarter. So a quarter, a half, 3/4, full, all the way. And there it goes, zoom. So we calculated the period, put that on the graph, and said, look at it go up and down, and it's come back to the same place. So that's the picture of it traveling through one period through x. Now I'm just going to draw a second period. So now we can see it do two cycles. Zoom, zoom. So this represents the block going like this. 1, 2. So that is an oscillation. So here the block is cycling through oscillations in space. But wait, there's more. This kind of graph can also represent velocity and acceleration. This is where it gets kind of cool and a little bit exciting. Instead of thinking about the position of the block, now let's think about the velocity. Now, where does this block have big velocity or no velocity or whatever? So what we want to think about is the energy. So remember, over here, the block has spring energy. Here it has kinetic energy, and here it has spring energy again, and here it has velocity again. So here, because there's no kinetic energy, velocity is going to be 0. Here it's going to have max velocity. Here it's going to have v is 0 again. When it comes back, it's going to have max velocity again. So let's call these positions 1, 2, 3, and 4. The only thing to think about is when is the velocity positive or negative. So we've said to the right is positive for x. So we're also going to say to the right is positive for the velocity. So that means in v2 it's traveling right, so that's positive. At v4 it's going left, so that's going to be negative that way. That's not so big, but you can see negative v max is v4 there. I can even calculate what v max is given the numbers up there. This is a conservation of energy concept. We say the spring energy initial is equal to the kinetic energy at position 2. So the initial energy is equal to the final energy. That means the spring energy is equal to the kinetic energy. So spring energy is 1/2 kx squared, and the kinetic energy is 1/2 mv squared. So this k is the spring constant there. The x is the max compression that it has. So that's the 10 centimeters there. M is the mass of the block, and v is the max velocity it will get at this position here in the middle. If I rearrange it, I get v equals square root kx squared minus m. Those halves cancel, let's take a square root. Now I'll plug some numbers in and see what I get. So I get 2.0 meters per second. I know students often like having tangible numbers when you're learning a concept, so I'm giving you what you want, a tangible number. So that is 2.0 meters per second. That's going to be the max velocity at this middle position there. So let's just write that down. So I'm going to say v2 is 2.0 and v4 is negative 2.0. Okay, so let's plot the velocity on there. So we'll start here. So at this position, where time is 0, we're going to say velocity is 0. Now we move over to here, and we say at that time, velocity is 2. I mark my y-axis from negative 2 to 2 meters per second. At the next position, that's going to be this one here, velocity is 0. And then the next position, back here, now my velocity is going to be negative, going that way, 2.0. Finally, I get back to over here, and velocity is 0 again. And that's one period of the velocity. I'm just going to draw a second period where it's 0, and then we go to 2 meters per second here, and then 0, and then negative 2 meters per second, and then 0. And we draw like this. Ba-ba! Very good. So I want you to notice a couple of things. Firstly, it looks just like a sine wave, but it's not quite exactly the same as the position graph. It's shifted over a bit. Basically, this one started here, and the position graph started at y was negative. So they're both sine waves, but they're shifted off a little bit. So we notice that they both have the same structure where they go up, down, and they have the same amount of time to do one period, but to do the same cycle, but they're kind of off from each other. And that's because it has spring energy here with a x position and velocity here for the kinetic energy. And it's like it's trading off spring energy for kinetic energy, so it's trading off x displacement for v displacement in this kind of dance. I can also draw acceleration on this graph, and it's also going to look like a sine wave. So now we're going to change the y-axis and put acceleration on there. So we've got to think about where is this block having acceleration is high or low or something like that. And so how do we think about that? So when we think about acceleration, we've got to think about forces. Remember Newton's law. Newton said F equals ma. So let's draw free body diagrams for just two positions to think about acceleration. So the acceleration is going to be here on the left, caused by the Hooke's law force, the spring force. So in the free body diagram, the main thing to notice is that there's a spring force going to the right, and that's going to cause an unbalanced net force, which is going to create acceleration. So we can go the spring force, which is kx, equals mass times acceleration. So we get the acceleration is kx divided by m. We can put some numbers in for that. So we get that the acceleration is 40 meters per second. So already we can put a point on my chart here, my graph here. I'm just going to sneak it in here. All right, acceleration is 40 that way. And which way is the acceleration pointing? It's to the right. So that's going to be positive. So we can put that on the graph. So the y goes from starting at positive 40, and it's here at time 0 for that position there. So we've just got to think about the second position and a free body diagram for that one. So there's just two forces acting on the block at this position. A force of gravity downwards and a force of normal upwards. So there's no left or right forces. We're assuming there's no friction here. So by Newton's second law, the sideways forces are balanced. There's actually no acceleration there. So I write the acceleration here is going to be 0. Now over here at position 3, the acceleration is going to be same as that position except negative. So it's going to be negative 40 meters per second squared. Joom. And now it's going to go backwards and forwards. So we can already draw the graph. So at time is 0, it's 40 meters per second, and then it's going to go 0 acceleration, then negative 40, and then 0, and back up to 40. So that's one period. And here it's located there again. Like that. And we're going to just do another period. So it's going to come down, down, up, up. And there you go. So it's tripping, it's cycling just like the other one. So notice that the acceleration graph also has this shape like this. And it has the same period, 0.31 seconds. And then we have another one. But also notice it's not quite exactly the same as either x or the velocity. The x1 looks the same, but it started negative and then went positive, negative. This one starts positive, negative, positive. And it's also shifted somewhat from the velocity. Again, here we have velocity but no acceleration. Here we have acceleration but no velocity. So there are these three graphs, and I'm going to draw them on top of each other so we can just think about them like that.